Hello guys, welcome to AAT Tech Talk. My name is Nandiwardhan Reddy from Informational Technology. My roll number is 20951A1248. Today's subject is operating a computer network. Uh, Today's topic is implementation challenges for software-defined networks. Let's come into the topic. Network configuration and installation require highly skilled personnel adapted configuration of many network elements, where interactions between network nodes, switches, routers, etc. are complex. A more system-based approach accomplishing elements of simulation is required. With the current programming interfaces and much of today's networking equipment, this is difficult to achieve. In addition, operational costs involved in personalizing and managing large multi-vendor networks covering multiple technologies have been increasing over recent years. While the predominant trend in revenue for operations has been decreasing, coupled with increasing scarcity of human resources and increasing cost of real estate. This perfect storm for service providers is leading to event interest in solution that can unify network management and provisioning across multiple domains. A new network model is required to support this. Absolutely. The term software-defined networking (SDN) has been coined in recent years. However, the concept behind SDN has been evolving since 1996, driven by the desire to provide user-controlled management of forwarding in network nodes. Implementations by the research and industry groups include Impletion proposed General Switch Management Protocol 1996 that embraced a framework for safe, resource-assured programmable networks 1998 and Internet Engineering Task Force IETF forwarding and control element separation 2000 and path computation elements 2004. More recently, Ethan 2007 and the Open Flow 2008 have brought the implementation of SDN closer to reality. Ethan is a security management architecture combining simple flow based switches with a central controller managing admittance and routing of flow. Open flow enables entries in the flow table to be defined by a server external to the switch. SDN is not, however, limited to any one of these implementations, but in a general term, for the platform, for clarity, SDN is described in this article with the Open Networking Foundation (ONF). Added definition. In this SDN architecture, the control and data plans are decoupled. Network intelligence and state are logically centralized, and the underlying network infrastructure is abstracted from the applications. SDN focuses on four features. First, separation of the control plane from the data plane. Second, a centralized control and view of this network. Third, an open interface between the service devices in the control panel and those in the data plan programming for the network by external applications. Functional applications such as energy efficient networking, security monitoring, and access control for operations and management of the network are represented at the top of figure 1, highlighting the user control management or management separation from the data plan. An application in this article refers to a service provided by the network operator. Detailed insight into every element of this architecture in figure 1 is beyond the scope of this article. Instead, the transition from the stational network to the state of the art in SDN today is presented. A key challenge is SDN. In SDN relates to separation of the control and data plane and maintaining career grade services within the framework. The architecture requirements to meet operational expectations in career grade Networks are scalability, reliability, and quality of services and service management arising from the control data plan separation. Challenges are discussed later in this article. A series of solutions to these identified issues are then studied, and the article concludes with the outline of our vision for the future of SDN. The, now, why SDN? The fundamental purpose of the communication network is to transfer information from one point to another. Within the network, the data travels across multiple nodes, and efficient data transfer is supported by the control provided by the network applications as servers. The control panel plane is responsible for configuration of the node and programming the paths to be used for data flows. Once these paths have been determined, they are pushed down to the data plane. Data forwarding at the hardware level is based on control information. In this traditional approach, once the flow management forwarding policy has been defined, the only way to make an adjustment to the policy is via changes to the configuration of the devices. This has proven restrictive for the network operators who are keen to scale their network in response to changing traffic demands, increasing use of mobile devices, and impact of big data. For this service focused equipment, SDN has emerged. Control is moved out of the individual network nodes and into the separate centralized controller. SDN switches are controlled by a network operating system (NOS) that collects information using the API in and manipulates their forwarding plane, providing an abstract model of the network topology to the SDN controller hosting the application. The controller can therefore exploit complete knowledge of the network to optimize flow management and support service user requirements of scalability and flexibility. For example, bandwidth can be dynamically allocated into the data plane from the application. Once the first packet of the new flow arrives at the switch from the sender, step 1, the switch checks for a flow rule for this packet in the SGN chase cache. Step 2, if a matching entry is found and the instructions associated with the specific flow entry are executed. Example, update counter, packet or match field, action set, metadata. Packets are then forwarded to the receiver. If no match is found in the flow table, the packet may be forwarded to the controller over a secure channel. Step 3. Using the sourcebound API, example, OpenFlow for CES, PCEP, the controller can add, update, and delete flow entries both reactively in response to the packet and proactively. The controller executes the routing algorithm and adds a new forwarding entity to the flow table in the switch and to each of the relevant switches along the flow path. This is step 4. The switch then forwards the packet to the appropriate port to send the packet to the receiver. SDN implementation opens up a means for new innovations and new applications. Dynamic topology control, adjusting switch usage depending on load and traffic mapping, becomes possible with the global network view. This introduces scope for networking wide access control, power management, and home networking, for which the network view is not beneficial but absolutely necessary. Furthermore, the network programming ability possible is in SDN allows seamless communication at all levels, for hardware to software, and ultimately to find users, network operators. Programmability makes applications aware of the network and the network aware of the applications. This enables greatly improved use of resources and open up the potential for new applications to the associated potential for revenue generation. Example, flow metering, in which cost planes can be defined based on the level of services. This is about this topic. Thank you for your support.